section 9.4, we're going to continue talking about series. The type of series we're going to be talking about in 9.4 is called an alternating series. So an alternating series is a series that decreases. So 0 is less than ak plus 1 is less than or equal to ak for all k greater than or equal to 1. And if that happens, then the alternating series from k equals 1 to infinity of negative 1 to the k plus 1 over ak converges. So if you have a sequence that, in essence, has a limit of 0 and it's decreasing towards 0, and it's alternating, right? I get the alternating part, right? So it goes back and forth between positive and negative. The ones we're going to be dealing with, you'll see them all have this negative 1 to the k plus 1 factor or some variation of that as part of the function. So if we want to be able to show that this converges, we can simply do it by showing that the limit is 0. You guys with me? I saw 2 people nod, so 2 out of 12. Excellent. All right, so we're going to do some examples. These are not very complicated to do because we've talked about how to prove that sequences have limits of 0 before. So here's our very first one. You see that it is alternating because there's that negative 1 to the k, right? We've got a k squared over k plus 1. And what we want to know is if this has a limit of 0. Now, you should, at this point, especially after 9.3, be able to look at this and tell me that the answer is what? Does this have a limit of 0? No, it definitely doesn't. Okay, this does not have a limit of 0. So it means that it's going to diverge. That's what that means. Okay? We just now need to show that that's what's going to happen. So far, so good? Yes, okay, good. All right, so we're going to find out what the limit as k approaches infinity is of k squared over k plus 1. The negative 1 to the k doesn't affect any of the sequencing. Okay? We want to know what the limit is of the sequencing that doesn't have the sign changing. So far, so good? You guys are really talkative today. All right, so tell me, from the last sections, you've had multiple sections where you've done limits now. What are we going to do in order to find out what this limit actually is? Multiply by what? You could use L'Hopital's rule. That would work. We actually talked about that in my office today, a couple of you who are in there. We could do that. In fact, why don't we do that since I haven't shown that in class, and you guys probably haven't seen that, those of you who weren't in my office today in a little while. Whoops. All right, so a reminder then about L'Hopital's rule. L'Hopital's rule says that if you're trying to evaluate this as the k value goes to infinity, and you either get infinity over infinity, if you tried to, so to speak, plug it in, or 0 over 0, then you're allowed to do what's called L'Hopital's rule. This one does have that feature. This is infinity over infinity, right? If we sort of tried to plug in infinity. It has the feature that both the top and the bottom go to infinity as the limit of k goes to infinity. So this, I'll put this sort of in a note over the side so that we remember that we're going to use L'Hopital's rule. We can use L'Hopital's rule because we have the infinity over the infinity. So we're going to do this then. Limit as k goes to infinity. And what in the world does L'Hopital's rule say next? Do you remember?
Take the derivative of the numerator and denominator.
Very good. So the nice thing about L'Hopital's rule says that we're going to do some derivatives, but we're not doing the derivative of the whole function. We're doing the derivative of the top and the bottom separately. Okay, so what is the derivative of k squared?
2k.
What is the derivative of k plus 1? 1. And then we would try the process again. We would see what happens if we quote-unquote plug in infinity. And if it's still infinity over infinity, or 0 over 0, then we would apply L'Hopital's rule again. This one isn't. What happens on this one if we take a look as k goes to infinity? We get infinity. The denominator is just 1. So this one is actually infinity. So the limit here is infinity. Infinity, last I checked, is not equal to 0. Right? Yes, today anyway. And so because this does not equal 0, the alternating series does not diverge. So the alternating series diverges And one way to do this is by saying by the kth term divergence test. Oops. Yeah, we'll just stop right there. That's sufficient. So we're using the divergence test to say that the limit here isn't 0. If the limit here isn't 0 of this featured part of the function, then according to alternating series test, that this alternating series will not converge, hence diverges. I'm so glad you brought up L'Hopital's because I hadn't used it in class yet, so thank you. Another option when we were looking at that is you could multiply the numerator and the denominator by 1 over k squared, or even by 1 over k would work on this particular one, and try to take those limits individually as well. That would work too. All right, let's take a look at this one. This one says to determine whether the series is convergent or divergent, just like the directions from before. It is alternating, right? Yeah, it's alternating. So we are going to be looking at the limit. Agreed? So this will be the limit as k goes to infinity of 2e to the negative k, or I'll write it as 2 over e to the k. So what about this one? What happens as k goes to the infinity? I mean, this is definitely not L'Hopital's rule because I've just got a 2 on top, okay? L'Hopital's rule has to do with getting zeros on top and bottom or infinities on top and bottom when we look at limits. So this isn't going to have L'Hopital's rule. This also doesn't have some of the like k squareds and k cubes of polynomials we were dealing with. We've got an exponential e to the k. So what are you seeing on this one happening? Where? Which part goes to infinity? The whole thing or a portion of it?
K goes to
Right, very good. So e to the k, if you'll remember the graph of e to the k, so to give you a visual, it looks something like this. As k goes, or x in terms of my graph, goes to infinity, the y value also gets infinitely large. So yes, the e to the k that's in the denominator goes to infinity. So what happens then to the function as a whole, or the sequence as a whole?
0.
Correct. So this one has a limit of 0. Agreed? I'm sorry.
It's all good. It's like,
Here you go. How's that one? Does that one look better? I think it's the same grade. Maybe not. All right. So this one has a limit of 0, right? So this sequence, specifically I'm talking about 2 over e to the k, or you could write it as 2e to the negative k, approaches 0 since e to the k approaches infinity. That's basically what you guys said. Thus, by the alternating series test, the summation from k equal 1 to infinity of negative 1 to the k, this alternating series of 2e to the negative k, will converge. Any questions on that one? Yes?
the original converted to 0, and so it equals anything else that's not convergent.
Yeah, we encountered a sequence that did this once. I think it was the very first section of work that we did, and it had the negative 1, it had that feature of the alternating business, and we talked about the fact that if it's bouncing up and down over the x-axis, but it's sort of like cone-shaped, it's decreasing towards the x-axis, that increase-decrease bounce actually makes it get infinitely close to the x-axis, and the positives and negatives start to sort of weigh each other out. Basically, is what's happening with the series. We didn't talk about it from series point of view, then we were looking at sequence. But the same idea is true. So since it's bouncing up and down around the x-axis, the fact that it's going to 0 without the negativeness of it, the alternating part of it, is enough to ensure that the series itself actually goes to 0. The series itself converges. Let me say it that way. Not goes to 0, but converges. It may or may not go to 0, but yeah. Now, this isn't true in general, right? It is not true in general that if the sequence goes to 0, that the whole thing converges. We've seen that happen before. Agreed? When we had the harmonic series 1 over x or 1 over k, it went to 0. But we looked at the way that those areas added up. We did it with rectangles, and then we also did it by the p-series test. And so 1 over k, while it goes to 0, its series, the summation from 1 to infinity or whatever you start with, does not converge. However, if you had that -1, that alternating pattern to it, and that were part of your function or your sequence term, then it would converge. Are you guys with me? So this -1 business being a part of this, alternating between positives and negatives, allows us to be able to make a conclusion in a much easier way. All we have to do is we have to look at the limit of the sequence itself. And if the limit of the sequence is 0, then the series is going to converge because it alternates. Now, we also have a very nice feature in Theorem 4.2. So Theorem 4.2 has the same criterion at the beginning. We've got a limit goes to 0. We have the sequence is decreasing, and we've got this alternating series that we're talking about, the summation from k equal 1 to infinity of this -1. Now, if this converges, okay, so we already found that not all of them do, of course. The first example we did diverged. But if this converges to some number s, then we can approximate the value that it's going to converge to simply by finding this partial sum Sn. And if we find the partial sum large enough, we will actually find what the series, converges to within whatever level of accuracy we want to be. Okay? We can be as accurate as we want to do. Now here's the cool thing. This is where we are able to actually use our calculators to help us with this process. You guys ready? Now, it's important to realize that this process that we're about to do works for what kind of series? Alternating. So this is not true in general. This is only when the series is alternating series. Okay? Alternating sequence, but we create the series from it. All right, you ready? There are two different types of calculators you may have with you. So if you have a TI 83 or 84, we're going to take a look at these. And it isn't necessarily that the 83 is old and then 84 is new. There are plenty of 84s that have the older processing that I'm about to show you as well. So most of you may know whether or not you actually have this because you're going to have certain abilities in your calculator. So do you guys know when you put in like an integral notation or something like that, does it look like your textbook looks, or does it look like funny math type on the screen? Funny math type. I've got one funny math type. So you have an older version, which is what I have too. Anybody else have that funny math type? You have one that actually looks like the integral or whatever like that.
Depending on which calculator I have.
And yours isn't working today, so you don't know.
My other 84 does.
Okay. If you're not sure, you'll be able to find out pretty quickly because we're going to actually pull up some features and you'll be able to see. So if you have an 83, 84, it's an older version like what I have. I'd like for you to hit, you can clear out what's in there, I'd like for you to hit second and then stat and then arrow over to math. So the second button, the stat button, and then arrow over to math. If you look down at number 5 and you have this type of a calculator, it's going to say sum with a parenthesis. Okay, so it's going to look just like this piece right here. Okay, so I'm going to see what y'all have. All right, so you have an older one? You already decided you did? All right, number 5. It may work as the older way than show me how to do it here. No. Okay. Yeah, choose number 5. You've got the newer version. And you pull it there too. All right. So if you have the older version, it will pull that up. It may do that as well if you have the newer version. We'll see very quickly when we get to the other option. All right, then you can hit second, hit stat again, and you go over the OPS, that's operations. And if you take a look down at number 5 again, it's going to say sequence, SEQ with a parenthesis. So now it should actually look like sum, parenthesis, SEQ, sequence, parenthesis, and nothing else yet. Okay, all the rest of this is blank. Everybody good so far? Okay. You good, Taylor?
Yeah.
You're showing Cameron since he's not participating today.
I have calculator.
I know. Okay. All right, so what you do next is you put in the function, whatever your function is in the calculator. All right, so if we're taking a look, let's see. We have number 3. We can just take a look at number 3 since you're on that page in your notes. We have -1 to the k. So we would put in a parenthesis, -1, into parenthesis, raised to the x power. And then that's part of our function. The other part of the function has times x over 2 to the x. So you're putting all your k's in as x's, of course. So this is entering the function. That's where we are right now. Next thing you do is we put a comma. Now you have to actually tell it x. I know that seems sort of strange, but basically you're telling your calculator x is my variable in the problem. All right? And then you put a comma. You put the lower limit of your sequence. So in the one that we're looking at, number 3, the lower limit is k equal 1. So we're going to put a 1. Then we're going to put another comma. And then the upper limit is this term that you're actually finding. Okay? That sequence, that highest valued term that you're going to take your summation clear up to. So for now, just put in, say, 10, just so that we can all have the same number. All right? So we're finding right now s sub 10, right? The summation of the first 10 terms. And once you've done that, you can hit enter, and it will tell you a value. Mine says -0.21875. Do I have some nods? I've got a couple of you. Did anyone say anything different? Everybody has that value. All right. Now, there's a couple of things you can do. This tells you the value to the first 10 terms. But we don't know that that's far enough. Obviously, it's just 10 terms. Okay? So we say, okay, maybe I don't want just 10 terms. Maybe I want 15 terms or 20 terms or 30 terms. If you've done this in the regular screen, which is what I just told you to do, what you can do is you can hit the second button and the enter button. And what that'll do is it'll pull up the previous line exactly like you entered it and allow you to make changes. So you can go back there and you can change the 10 to a 15 or the 10 to a 20. Okay? So that's really nice. However, it might be even nicer if you wanted to do a whole bunch of them to do it in a table. Okay? If you want to do it in a table, the only difference is you enter all the pieces the same except for after lower limit, you put comma x. And so that tells your calculator that when you go into the table and you put in, say, 5 in for x, the upper limit's now 5. You put in 50 in for x, the upper limit's now 50. So your table can be created so that you can see all of those values at the same time instead of re-entering one at a time. Even with the changing that I'm doing, that's going to take longer than if we did it inside of the table view.
So when you have it just on your normal screen,
Yep.
X, you just go to the table, or
It won't work in the normal screen. You have to put it in the graphing screen, like where you put y equals. Yeah. So this one, I should have written it in here like that. Basically, what you're going to have is you're going to have y1 equals right here. And you're going to put that into the y1 or y2 or whatever it is in your calculator. Okay? So let me run through the newer version for those of you who have that one with you. And those of you who do have the 84s, double check to make sure you may have this too. I can't tell for sure on your operating system, so take a look. On the newer version, if you hit, and I don't have one with me, so you're going to have to tell me if this works because I got these directions online. I wasn't able to actually check them. It does. I've got some answers of yes. If you hit math and 0, okay, then you should come up with a summation. I mean, it actually looks like a summation. It has a blank box down here and a blank box up here, and it should have something next to it blank or something like that, right?
2 blank boxes for the variable on the bottom.
Ah, like this.
Yeah.
Okay. And does it have a blank box over here?
Blank box equals blank box on the bottom.
Oh, I see what you mean.
So you put the variable on the bottom.
Does that look right? Does not? Okay. So this is fabulous because you know exactly where to put what on this version, right? And you can do this within your Y1 menu as well. So if you go into this, you can actually put inside of Y1, you can choose this operation. You should be able to. That's what I'm told. And you should be able to put in down here x equals, say, 1 for the one we're working with. And then the top value you would put in as x for now. Okay? so that you can do it within the table if that's what you're wanting to do, and then your function that you're working with over here. With the -1 raised to the power, it needs all of it, the exact sequence that you were given, not just the part that's not alternating. You need all of it. So what I want us to do is I want us to do this value together, the one we just put in, but I want us to do it in the table so that everybody has a chance to try that. So go into your table. So hit, go into y equals first. So hit y equals where it says y1. And after y1, use your version of however you have to do it, whether it's the sum with the parentheses, sequence, and parentheses and all that, or if you have the newer version, the one where you actually have the summation keyed in, do it that way. Okay? I'd like for you to enter that. And once you have, you're going to go out to your table. And we're going to create a table. And not because this is anything specific, but just that way that we can all make sure that we're on the same page and nobody has any errors or questions as they're working. We're going to put in the x values that I'm going to list. So we're going to do 5, 10, 15, 20, and I went up to 25. So go ahead and put those in underneath the x, and then you can actually go over on your calculator's table screen to y1. Now, is anyone, when you get there, if you're not able to actually put in a value you want into the table, let me know and we'll fix that.
I can change the.
Yeah, that's what our provided
If you go math zero, so you don't have the newer text type in there. Math type. Here's your Okay, so right now you're just you can't enter values of your table. We're gonna do it.
Now you have to do second stat.
Second, do this right here. Second, you go to 5. Oh, the person says ask. Maybe you start entering. All right, go ahead and second table. And you would type it, you go to whatever as much you want. There you go. So do 5, 10, 25. And just keep it. That makes. No, it's just that. Second. Yes. Okay, so then we're going to second window. We're going to make this first auto say ask. Here, no equation. And then go to the interest. And then we have more. And then you can choose enter. Is yours working? I said, oh, I like going on here. But inspired.
Right, so this is the citation. This is
Not that test, right.
If I have this with the inspired.
That's fine.
Okay.
Shelter graph. Times K.
Yeah.
Maybe it accidentally did that.
You should put a lot of
All right, so go ahead. All right, so go into that.
Yeah, if you use parentheses, if you're going to use parentheses with more fractions, they can also use yeah.
Okay, we may have to look at your calculator together afterwards. Maybe there's a technical issue. I'm not seeing that. Okay. Did you guys get values for Y1? I mean, from the table anyway? Yeah? Some of you are nodding. Some of you didn't have calculators, I know, so you're going to fill in what we've got. I'm going to fill in what I have, and we're going to make sure that everybody has those same values, that we're on the same page. The first one we actually did a little bit ago, or actually we did the second one. So I've got negative 0.28125. If I go down the screen, I've got negative 0.28. I didn't say it right again. 21875. If I look at 15, I've got negative 0.2222382. This textbook seems to like 6 decimal places in most places, so I'm going to record it to 6 decimal places. And the next one is 0.223. 2, 2, 1, 6. And the last one I've got, if I go to 25, is 0.222. I think I've got 6 2s, I think. This is what I have. It's wanting the sum to be within 0.01, so to the second decimal place be correct. We see several locations in this table already towards the end, 15, 20, and 25, that all have those same first two decimal places, the same value, right? So this series, correct to within 2 decimal places, converges to negative 0.22, which is what we're asked to find. Now, there is nothing special about these values that I picked, but you need to show something in your table that shows that they're not always negative 0.22, right? Because if I chose values that were much larger, like let's just say I started with 20, and then I did 50, and then I did 75, they're all going to say 0.2222. That's not going to show that it actually was never not 0.2222. You guys with me on that? So you want your table to actually show that, yes, it's not always this value, and yes, it is getting closer to this value as I move down my table. Okay? So number of entries in your table, I would say a minimum of 3 or 4, probably 4 would be appropriate. So if you've got fewer than 4 entries in your table, you probably need to do the next entry or a previous entry in order to make sure that your table really shows what you want. Yes, Tyler?
Our homework is to copy the table.
Yes, I want you to draw in the table, exactly. Thank you for asking. Yep. So draw in the table when you're doing a problem like this from your homework. Yes?
You want like 5 points or just?
As long as you have at least 4. That's what I was saying. If you've got 4 lines in your table and it's really showing that it's really getting close to the 0.22, that's probably okay. So for instance, if I hadn't had this last one right here, I'd already have had enough to really verify that, yeah, I've got 3 entries in my table, 2 entries in my table where I've got that decimal point of the 0.22. I keep saying, not saying the negative, but it's there, negative 0.22. And so, yeah, that would be okay. So we're showing by this table, even without the 25, that yes, in fact, my values didn't always equal negative 0.22, and they are, in fact, getting closer and closer to that. And you can see toward the end that I've got multiple 2s in a row now showing that feature. Any other questions? All right.